It's claiming to still be recording. Everyone's still here. I don't know what's going on. How's my internet? No, it's good. That is so annoying. I know the entire universe, the Wi-Fi universe doesn't want this class to happen. Okay. Try it one more time. If it happens one more time, I give up. But I'm willing to try it one more. I'm really sorry. Okay. It's annoying too, because I have to get it all set up so I can see everything every time. It's annoying for me, not you. Okay. So we can visualize this trade-off between the recall and the or the specificity by visualizing them on as a graph. So, and that's going to help us decide what an appropriate cutoff would be. Or maybe if we have some trade-off in mind, then that's going to help us determine the trade-off. So the trade-off between the recall and the specificity. Using, and maybe I should give it a name, using an ROC curve. Using an ROC, which is the receiver operating characteristic. The textbook had a fun little footnote about where it came from. And if I'm remembering correctly, it was from air traffic controllers, so airplanes, when they were first trying to figure out if they were correctly identifying airplanes on the radar or something. So they knew they could see if there was an airplane, but did the radar pick it up, right? And so hence the receiver part of it, I think. But anyways, usually we just call it an ROC curve. Right? So an ROC curve, or graph, I guess, puts typically the recall on the y-axis, because that's the recall, remember, is the number of ones that were correctly classified as ones, and against the specificity. And what we're going to find is that as we change our cutoff value, right, then there's going to be a kind of a change. So what we have as a guide is this diagonal line is going to be what would happen. So that's representing just random classification. Right? You're a 0, you're a 1, you're a 0, you're a 1, you're a 0, you're a 1, you're a 0, you're a 0, you're a 0, you're a 1, you're a 1, you're a 0, right? Just random classification. So this is the equivalent of a random chance classifier. Okay. I feel like the recording button looks different now. Maybe it was trying to update or something stupid, but hopefully it's still recording. Okay, so that's our random chance classifier. And then what's going to happen is we're going to get this kind of ROC curve that might look something like this. What we want is we want this curve to be lifted off of the random chance curve as much as possible. And it's going to move up into kind of as high off of the curve as we can, right? And so we want, and maybe I should put it over here so it can stay on the same page. We want the ROC curve to be as far from the random chance classifier as possible. We want the ROC curve as far from the random chance classifier as possible. Okay. So one way that we could really zero in on that is what we call the area under the curve metric, the AUC. So the area under the curve is the area under the curve. And if you think about calculus again, man, that's a lot of calculus, of course. There's always calculus in the background, but we don't have to use it, but it's good to know that it's there. The area under the curve is what? It's an integral, right? And so you'd have to integrate and subtract the random chance. And so the area under the curve I guess it's area underneath the curve, which is, and I should capitalize curve, the AUC is a metric that we can use to evaluate our model. So area underneath the curve is a metric we can use to evaluate the model, right? So what happens is an AUC of 0.5 is going to be considered ineffective, right? Because 0.5, well, that's the random chance classifier, right? Because it splits the this area. Because these are proportions, right? We're restricted between 0 and 1. I didn't show that, but we are, right? And so the total area here is 1 by 1. And so half of that is taken by the random chance classifier. You don't want to exceed your, have your specificity higher than your recall, right? You're interested in the ones. So then an ineffective AUC would be 0.5. And the AUC can go to 1, right? So it moves to 1, and that would be a perfect classification model. Okay, so then it's going to be on a scale from 0.5 to 1, and so maybe 0.6 is not that good. Depends on your other models, right? You want to pick the one with the highest value, even if it's not high, that's your best one. So it's hard to say that, oh, this AUC, it has to be bigger than this, just like R squared, right? Maybe R squareds are only between, 40 and 50%. That's not good. But if it's the best one, that's the best model, right? Okay, so those are some of the metrics, and we could visualize the AUC, but it's also just a number, and so I would prefer to focus on just the number. Okay. All right. So what we talked about before was, what if we have these rare cases, right, that we're trying to figure out, right? So a lot of the time we're trying to model rare cases. So a lot of the time, we want to model rare cases, right? Rare cases, right? Which translates to our sample usually only has a few ones and the rest are zeros. So it would mean that our sample has many zeros and very few ones. So you don't want to build a model just based off of this data. So what can we do? So we call this an imbalanced data set or imbalanced data. We call this imbalanced data. So what can we do to deal with imbalanced data, right? If we just built a model, then that model is going to be learning from a bunch of zeros, right? That's not good, right? And so, well, when I said that, I thought about, you send your kids probably to the best school that you can because you want to learn from the best. Right. So if you're trying to pick up on the ones and you train it on a data set that's mostly zeros, then that's going to override all the information that you have from the ones. Right. And so what are some of the things that we can do? So to deal with imbalanced data, we have a few options. We have a few options. And there are many more beyond this, but these are kind of our go-tos. It's nice to have a set of go-to options. And if you're still finding that that's not working, then of course you'd have to do a little bit of research and you'd have to look into some of the other methods that you could use, right? And maybe they would be better, but it's good to have a kind of a core set of tools. So the first one is undersampling. Undersampling just means you're going to just take all the ones that you can, right? As many ones as you can, and have approximately the same number of zeros. That's undersampling from the total sample, right? So you take just a few of those zeros. That means you're missing a lot of the other zero information, right? That zero information, yeah, so there is a little bit of bias there because then you're missing information, right? It doesn't really do anything, but it does create bias, right? Because then we're saying, oh, well, I don't care about that information. I have it, I'm not going to use it. That's silly, right? And so undersampling, and blue, is going to be, so undersampling is sample roughly as many zeros as there are ones, right? But this ignores many zeros, right? So here, this ignores many zeros. So that's bad. That's why I wrote it in red. Okay. So that's one of the options though, right? And then you would have the ones on a level playing field and you'd be able to see those ones. Another option, or kind of two options, is oversampling. or up-down weighting. Or up-down weighting. Kind of the same. Okay. So if we're oversampling, then what we're doing is we're resampling those ones, right? And so I'm allowing all the zeros to be in my sample, but then I'm resampling, or I'm giving a heavier weight to all the ones, right? To kind of recreate them. You can see the problem there, right? Because then you just have a bunch of these ones floating around, and it works. It does work. It's just that you have the same observations that you would have already, right? And so you're just making more of those same observations, right? And so so oversampling or up-down weighting, which are the same, is when we resample ones so that they're more dominant, right? Or not necessarily dominant, but so that they're to increase the number of ones. So resample ones to increase the number of ones, or you can apply a weight. So any zeros are only worth 1, whereas any ones is going to be kind of magnified by however rare it is, right? And so so you use 1 over p, which the p is how many ones do I have in my total sample. And then if I take 1 over a small number, it becomes a large number, right? And so you can apply a weight, or apply a larger weight to ones than zeros. Right. And so here the problem is that we're just recreating ones we already have. Recreating ones we already have. So what's another, and not to jinx it, but it hasn't booted me out ever since I said this is the last time I'm going to try it. So home stretch here, I'm going to go for it. So the next one is kind of more sophisticated. It's called SMOTE, and I cannot remember what it stands for because I didn't write it down. So I'm going to look it up here just briefly. Sorry. Synthetic minority oversampling technique, obviously not obvious. Synthetic minority oversampling technique. You can just tell by the name that this is going to be one of those kind of relatively new things that we've come up with computers, right? That we really weren't able to do before, right? So it's one of those things. It does rely on k-nearest neighbors, which we haven't talked about in this course, but I know that you've seen at some point, but we're not going to talk about it until the next chapter. So I'll just kind of hold off a little bit. And in general, what it does is it generates a fake record for the ones based off of its nearest neighbors, right? So it kind of looks at, okay, well, what was the predictor for X1 for these guys? Oh, okay, I'll randomly pick one of those, and then I'll be one of these, and I'll be one of these. And so we're kind of generating data that's based off of data that we already have. And so it generates, that's not a word, generates new values of one, new values of ones using the predictors from existing ones, using predictors from existing ones. All right. So it kind of generates these synthetic ones based off of it that have similar predictors to what we see. And how we just talk about similarity is by the nearest neighbors algorithm. But we haven't talked about that yet, so we'll refresh on that, but that's not till the next chapter. Okay. So the very last thing that I wanted to say was once you have these probabilities, right, of being in class 1, which means you have the probability of being in class 0, right, then you definitely want to consider the cost of misclassifying or correctly classifying a 1 or potentially a 0, but usually a 1. Right. And so beyond classifying purely based on the probability of being in class 1, which is what our model gives us. So beyond classifying a record purely based on the probability of being class 1, and I'll put in brackets, which is what the model yields, right? So instead of just looking at that probability, right, then we also need to consider the expected return, right? What's the, how much can I gain off of correctly classifying a 1, right? If I pick up on a real customer, a real potential customer, how much could I potentially gain there, right? Versus, oh, okay, I tried to pursue that person as a customer, they didn't want to go for it, oh well, right? And so there's kind of costs involved as well. So beyond classifying a record purely based on the probability of being class 1, we should also consider the expected return for each classification. For each classification. Okay, I'm all out of time. You guys made it. I'm so sorry about all the glitchiness, but nice work. And that is where we'll finish off. Yeah, it was both of our faults. If you have any questions, let me know, but I'll stop this recording and see you next week. Oh yeah. See ya. Yeah, I'm just going to stop this recording, but it's telling me I do not have the rights. Record.